Welcome to another session of our look on calculus or treatment of calculus. We're still on the topic of vector spaces. This is the fourth session, and today we would like to focus on the spaces and subspaces. So, for example, if we have our Euclidean space, a three-dimensional space, and then we do have a vector subspace, which are simply planes that go through the origin. When we do a translation of that vector space into subspaces that don't include the origin, then we have what we call the affine subspaces. Now, a combination of all these planes that include both vector subspaces and affine subspaces, this is what we call hyperplanes. So today we'll just go slowly, building on a progression from what a mapping from a point in space to a real number combination or coordinate, and then from there we'll look at the equation of a line, we'll look at the equation of a plane, and then we'll see the point for which the equation of a plane amounts to a vector subspace, and then we'll see the linear or the parallel translation of that vector space into an affine subspace, and then we'll introduce the topic of hyperplanes. So it's going to be an interesting journey. I hope you enjoy holding it in. If you have any questions, feel free to reach us through the comment section, or you can email us directly. We'll leave the details in the description. But other than that, let's get into it. So our problem going forward is, how do we relate a point in space to a number or to a real number? For example, let's assume that we do have a line as our space, and then we have to associate any given point on the line to a number. So this is done using what we call coordinate correspondence, right? So you have to build a coordinate correspondence between a line and a real number, R here, and this is determined by choosing arbitrarily a point on that line L to be 0, or what we call the origin. And then above that, you have to choose a unit point. That unit point could be 1 meter from the origin, or it could be 1 centimeter, or it could be 1 foot. But you got to choose a unit point, and we call that unit point Q, to be distinct from O. Then now what you have is, once you have that Q, you could obtain any arbitrary point on that line, for example, let it be X. And if that point X is of magnitude, or is of distance, magnitude of X, and it's important to have this magnitude symbol because this X could be negative or positive. So that point is going to be associated to the real number X here, which is obviously a real number. Now this X could be positive, it's on the right hand side of the origin, or it could be negative, it's on the left hand side of the origin. And so this X is going to be the magnitude of X times the unit point, or the unit distance from O. Right? Now the mapping from the space X on the line to the real number X is what we call coordinate correspondence. right? Looking at a coordinate correspondence between the Euclidean space. The Euclidean space is a three-dimensional space that we are so familiar with, and a Cartesian vector subspace, R to the 3, is also one of those things that we are probably familiar with. The problem of transforming a point or relating a point in the Euclidean space to the three-dimensional, the Cartesian vector space. First, we have to consider an arbitrary 0 point in the Euclidean space. And then, as we said on the line, so here we are going to look at three-directional treatment, and so we look at 3 unit points, Q1, Q2, and Q3, in such a way that they don't lie in a single plane. So they're going to be perpendicular to one another. So we have origin O, we have point Q1 in one direction, Q2, that's the unit point in the other orthogonal direction, and then Q2 and then Q3, which are orthogonal to one another. Now, if we draw lines along Q1, the Q direction, and then to Q3, so that they are L1, L2, and L3 respectively, then what happens is that these lines here drawn through these unit points are called coordinate axes. So if we consider any point x in the Euclidean space, we could do one thing, and that is we draw a plane through x that is parallel to the axis or the coordinate axis L2 and L3. So that's the plane we have there. And that plane crosses L1 at a point in space, capital X1. And then in a similar way, we could draw a plane that's parallel to L1 and L3, and that cuts L2 at a point capital X2. And then the same way, we draw a plane that is parallel to L1 and L2 that cuts the coordinate axis L3 at point capital X3. So we could describe that point X using these three numbers, three spaces, X1, X2, and X3. What we've done here is we've developed a mapping theta that relates a unique point in space to a unique vector in the vector space, right? In other words, we're relating a point in space in the Euclidean space to a real number coordinate triple. We also call theta the coordinate correspondence defined by the axis system that we just showed. And interestingly, the unit point Q1 on L1 now has a coordinate triple, delta 1, which is 1, 0, 0. The unit point Q2 on L2 has this coordinate triple, delta 2 of 0, 1, 0. The unit point Q3 on L3 has this coordinate triple delta 3, which is 0, 0, 1. Some important properties of this mapping. We say that this mapping theta is a bijection, and by that we mean that a unique point in space, in the Euclidean space, e to the 3 is related to a unique vector in the vector space R to the 3. Similarly, a unique vector in the vector space R to the 3 can be related to a unique point in space. So there's a forward one-to-one, but also there is a backward relationship. So it's a bijection. Similarly, if we have two line segments AB and XY that are equal in length and parallel, and the direction from A to B is the same as the direction from X to Y, that happens if and only if in the vector space or in the coordinate triple space, vector B minus A equals to vector Y minus X. That is in the vector space or in the coordinate triple space R3. Another important point is that there's this terminology, a directed line segment. What a directed line segment is, it's a geometrical line segment that has properties imbued to it. So together with the choice of the length, we have the choice of direction. So it could be, for example, if you have AB, you could choose to look at the direction from A to B or the direction from B to A. So that's what a directed line segment is. You have the aspect of length to it, but also the aspect of directionality. Just to put some emphasis on what we've talked about, if we interpret AB as a directed line segment from A to B, and if we define the directed line segment AB and XY to be equivalent, the way we write it is AB tilde XY. So the thing we could do is, if they're equal in length and parallel, then we can express this in the following way. And this is what we just mentioned previously. AB tilde Y, in other words, AB and XY are equivalent if and only if B minus A equals to Y minus X. So we talked about that previously. Now, if X is not 0, is not at the origin, then Y is the line through 0 and X in the Euclidean space if and only if Y, now we're looking at the vector space, Y is equals to a real number T times the vector X. In other words, if we have a line or X and then you extend or that line or X to a point Y, or between O and X you have a point Y, then it means that the vector Y that corresponds to the point Y in the Euclidean space is the same as the product of a scalar T and a vector X corresponding to the point X in the Euclidean space. Now, for some T, that is obviously a real number. Moreover, this T is the coordinate of Y with respect to X when we consider X to be a unit point on the line through O and X, right? So if the axis system in e to the 3 or Euclidean space is Cartesian, that is, if the axes are mutually perpendicular and a common unit of distance is used, then the length or X, the length from O, the origin, to the point X in space, that segment has a length that is called the Euclidean norm on the vector space R3. Therefore, OX is considered as the cumulative sum of the squares of the coordinate points and then the square root of that cumulative sum, and that is called the Euclidean norm. Let's just to touch on some of the things. Let's play with some triangles here and there. So we do have the Euclidean space, and then we have origin, and then we have a unique point in space x. Obviously, the segment or x can be decomposed so that we have a point at the base in the xy direction, or in the base plane. That point is y, and that point y also can be broken down into obviously a component on one of the lines, and so we have this perpendicular drop from x to y, and then a drop from y to one of the axis that's perpendicular. And so there's a distance x1 from the origin to a point from which we drop y2 on one of the axes. Similarly, the length from that axis to y can be considered to be x2, and so that corresponds to a point on this other axis as shown here. And then obviously the height xy corresponds to a length x3 on that vertical axis. So we have the distance r, and then we have the distance s. S is certainly the square of s. You could look at it as the square of the Euclidean norm, but also you could look at it from the angle of Pythagoras theorem, where we have s squared is equals to x1 squared plus x2 squared. So the Euclidean norm still holds. And then we have this right angle triangle involving s, r, and x3. So r squared or x squared is equals to r squared which is equals to s squared obviously plus x3 squared. So you could spend some time and see that the Euclidean norm also holds there. Similarly, if we do have this other right angle triangle, we have O as the origin, we have x, we have y, which is just simply an inversion of what we have here. We have a vector OY or vector y. The scalar product of that can be represented as y, which is OY squared. Again, going back to the Euclidean norm, the scalar product of vector x is OX squared, and then since the vector here is y minus x, the scalar product of that is equal to the Euclidean norm xy squared, the square of the Euclidean norm. So taking the triangle OXY, the segment OX and OY are perpendicular if and only if the scalar product XY has the value 0. So that's an important property. The scalar product of two perpendicular vectors is 0. Yeah. And then you can go further and look at this vector relationship, and you'll be able to prove that yes, the scalar product of two perpendicular vectors is 0. So an important concept on scalar product, or important property, is that scalar products are linear as functions of either vector variable. So if we have a a scalar c, that's an arbitrary real number, multiplied by vector x plus scalar d times vector y. When this combination is multiplied so that we get the scalar product of these two sets of vectors, then it's easy to see that that is the same as scalar c times the scalar product for x and y plus scalar d times the scalar product of y and z vectors. So it's very easy to see that, but we can use the properties we've already seen to find equations of lines and places in the Euclidean or three-dimensional Euclidean space. So let's take a rectangle here where we have the origin O, and then we have a given point B, and then we're trying to find an equation of a line that passes through a point, an arbitrary point X, but also we're given point A. So how can we find the equation of such a line? So we know that the vector or the line along X and B is parallel to the line along A and O. So the vector Bx and vector OA are parallel, but we don't know the lengths and how those lengths are related. So we can use an arbitrary constant t to signify that. So we have A and B are given, A not being equal to 0, and then the line through B and parallel to the segment OA contains the point X only and only if there exists a scalar t such that the vector X minus B is equals to the product of the given scalar t and the vector A, right? Such that the equation of the line through X can now be, by reorganizing this equation, be equal to the scalar t times the vector A plus the vector B. This vector equation is equivalent to three numerical equations. Xi is equals to AI plus T plus BI, where the i's indicate the x, y, and z directions, 1, 2, 3. Normally, these equations are called the parametric equations of the line. Equation called parametric equations of the line, they are called so since they present the coordinate triple x of the varying point on x of x on the line as a function of the parameter t. So t is a parameter that is there, and so that's why we call these equations parametric equations. Just a quick example. Let's derive the equation of a line that passes through 2 points, A and B, where A is 5 and 5, x and y, B is 3 and 2, x and y, in the two-dimensional space. So we'll draw a line there, and we have point A and point B, and then we have an arbitrary point x consisting of x and y. So we know that vector different x, y, so xy minus 5, 5 is the same as vector AB, right? The vector from A to B times the scalar t. So this becomes xy minus 5, 5 equals to t times negative 2, negative 3. And so we have a relationship here, xy being equal to t, negative 2, negative 3 plus 5, 5. We can take the x and y separately. So we have x being equal to negative 2t plus 5, y is equals to negative 3t plus 5. And so x is the same as, so we can reorganize this first equation so that t is suddenly x minus 5 over negative 2. Now substitute this value for t with respect to x back into the equation for y. And so we have y equals to negative 3. In place of t, we have this x minus 5 over negative 2 plus 5, and that results into an equation 2y, since this negatives cancel, so multiply 2 across, we have 2y equals to 3x, and since we have negative 3 times negative, 3 times 5, because the negatives are being cancelled out, is 15. Negative 15 plus 5 is equals to negative so since we have this 2 multiplied to 5 is 10, so we have negative 15 plus 10, which is negative 5. So 2y equals to 3x minus 5. That's the equation of the line. So in such a simplistic way, you can use vectors to derive the equation of the line without having to go through the extra steps. We've seen that we can derive the equation of lines using vectors, but also we can use vectors to derive the equation of planes. For example, again, keeping to the three-dimensional Euclidean space, and we have origin, or we have a point A, so we have a line segment OA, and then we have a point B, and so an arbitrary point X in space. So we have a line segment OA that allows us now to define a plane that contains both a given point B but an arbitrary point X that will still be contained in that plane. So that point, arbitrary point X, represents any point on that plane. So if this plane happens to be parallel to the vector b and x, or bx, that vector bx is perpendicular to OA, since we know that point A, then we can use the scalar product approach, where we said if vectors are perpendicular, in other words, vector bx being perpendicular to the vector OA, or vector A, we say the scalar product of that equals to 0, as shown here, right? So using the linearity aspect of scalar products, vector x minus b and a, when multiplied so that we get the scalar product, is the same as the scalar product of x and a minus the scalar product of b and a. Since b and a are given, we can reorganize this in such a way that BA is the same as a constant L. So the the scalar product of x and a, since x is not known, is this linear functional AI times xi, where I takes 1, 2, or 3, sum together, being equal to a constant. And this is the equation of a plane. It's a linear functional that is equal to a constant L. Thus, a point x on a plane through B perpendicular to the direction of LA happens if and only if the equation above holds for its coordinates triple x. If a is not equal to 0, then we can show that any sets of points x in the Euclidean space whose coordinate triples x satisfy the scalar product x and a equals to L is a plane. It's easy to show that. Previously, we saw that a transformation from a vector space x to this linear function or to the linear combination we see here is the most general expression of a linear function or f on the vector space R3 and a number L, such that the equation M is fx taking this vector into the real number L. Given any non-zero linear function or f on a vector space R3 to the real number and any L that is a real number, the locus fx equals to L is a plane M in the Cartesian or three-dimensional Euclidean space. The coefficient triple A can be obtained from F by AI being equal to F in bracket delta I. And delta I here, these are the basis, the vectors, the unit vectors that we saw previously. Since fx equal to the linear combination here, then we can say that by using the linearity, the linear combination of f to delta I is equals to the equation of the linear functional, giving us a relationship AI being equal to f delta to the I. So it's a pretty straightforward, since we know the basis x being the vector x is a span or it's a linear combination of the basis vectors. But then if we feed that into the equation of the plane, the linear functional, and we know linear functional is also a linear equation, so there's some linearity there. We can now take f to be focused on the basis vectors, and clearly we see that alpha I is the same as the function or the linear function or the function f on the basis vectors. So one thing we could also say that if we have a line that contains points O and X, and that is transformed in a parallel fashion into a line that contains B and Y, we can say that the vector X is equals to the vector difference Y, or vector difference of Y and B, and such that this happens to be a transformation where if X is transformed to Y by adding a given vector B to the original vector X, right? This is called parallel translation. Parallel translation. And parallel translation here, as we see, is just an addition of a given vector to the original vector. Under parallel translation, planes map to parallel planes, and lines map to parallel lines. So it's important to know that this is equivalent to just adding a constant to a given point in space. Parallel translation means that you're transforming a line to a line and to a parallel line and a plane to another parallel plane. If we consider a plane M with the equation f of x equals to L under the translation of x onto y, such that y equals to x plus b, then we can rearrange things such that x equals to y minus b, and that happens when the point x on the plane happens to be there if and only if the translate y also satisfies f of y minus b equals to L. Now, using the linearity property of linear functionals, we can now say that f of y minus b is the same as f of y minus f of b being equal to the constant L. And so if we add f of b on both sides, we get a new constant on our right hand side as L prime. Thus, f of y is equals to L prime, which is also a plane N. So in other words, the translate of plane M is plane N. We can transfer all these amazing terminologies from conceptualizing it in the Euclidean space to the corresponding three-dimensional Cartesian vector space. And that's talk of set of ordered triples x satisfying fx being equal to L as a set of points in the 3D Cartesian vector space, forming a plane in the R to the 3 space, or into the Cartesian space. So the mapping x onto x plus b, we call that parallel translation of the space R to the 3, or the Cartesian space, through B. If the equation M is f of x equals to L, then the plane M goes through 0 if and only if L equals to 0. In this case, M is a vector subspace of the Cartesian's vector space, and that is considered to be null. We saw what a null space entails. A null space is this space where the transform is 0. And so the set of vectors that when translated to this, or when applied to the function, is transformed to 0, the set of vectors in the domain are the null space of that transform. So this is the null space of F, and this now allows us to now define different manifolds or different subspaces within the Euclidean space. This actually sets the stage for very interesting subspaces that we'll look at. For example, the line T A plus B, where T is a real number, is the translate through B of the line T A, and the second line is a subspace and the linear span of one vector A. So the line that passes through 0 is definitely a subspace, and that is just a linear span, which is a linear combination of the base vector A. That we've come to know is that planes and lines in the Cartesian vector space are translates of subspaces. A plane in the Cartesian vector space R3 through 0 is a vector space which is two-dimensional in a strictly algebraic sense. Also, in this same Cartesian space, there are no proper subspaces other than planes and lines through 0. But in a vector space V, with dimensions greater than 3, n greater than 3, proper spaces occur with all dimensions from 1 to n minus 1. The translates of vector subspaces, in other words, those linear functionals with, null subspace, they are called affine subspaces. So it's important to know that if V is a finite dimensional space with dimension n, then the null space of a non-zero linear function of f is always n minus 1 dimensional, and therefore it cannot be Euclidean-like two-dimensional plane except when n equals to 3. An important concept here is that we saw that vector spaces are those planes. I wouldn't want to use the word planes, but those linear functionals that have null spaces, but a combinations of both these planes that pass through 0 and the affine subspaces that amount from linear translation or a parallel translation of these vector spaces is what we call hyperplanes. So hyperplanes is a term that combines the null space or one of their translates. A hyperplane is a set of which the equation fx equals to L holds, where f is a non-zero linear functional. So that's the gist of it. So we know what affine subspaces are, we know what hyperplanes are, we know what vector spaces or vector subspaces are. So in other words, in the 3D Cartesian space, hyperplanes are simply ordinary geometric planes, but in two-dimensional Cartesian space, hyperplanes are just lines. Right. Just as an example, the vector space R to the n, or the n-dimensional Cartesian space, is spanned by the n unit vectors. And so we have these unit vectors: delta 1, 1, 0, 0, 0, delta 2, 1, 0, 1, 0, 0, 0, 0, all the way up to delta to the n, 0, 0, 0, 0, 1. And so any vector in that space is just simply a linear combination of these unit vectors for all x's that are members of that space. We can also say that R to the n is just simply a span of the unit vectors or the basis vectors. So that's just another way of looking at it. We don't have much to add on this. I think this is an appropriate time to close this. Thank you so much. Until next time, stay locked in. If you have any questions, please feel free to leave them or reach out. We are here to learn and just grow. If you haven't subscribed, please press on the subscribe button. We'd like to grow with you. I would like to learn from you going forward. Bye bye.